We'll now take a look at the last theorem in this particular section, which is going to be a very simple theorem overall, at least compared to all of the previous ones that we've seen so far in Chapter 5. Here's what it says. Convergence and divergence of a series is not changed by deleting a finite number of terms from the series. Now, I'm actually going to go ahead then and try to think about some quick examples here, right? So let's suppose that I had a series that, I don't know, let's just make up a series that looked like this. 1 plus 2 plus 3 plus 4, on and on and on forever. Now that series either converges or diverges. And what this theorem is saying is that if I was to go through and pick out a finite number of things to just erase from this addition problem, maybe I would just be like, I'm just going to erase the 4. Well then, that shouldn't affect the overall answer. Because if the overall answer here was a finite number, maybe all of this added up to 6. I don't know. And if this added up to a finite number and then I just took a little bit away, that's still finite. But if this was infinite and then I took a finite amount away, well then it's still infinite. So I have something kind of like that operating here. Now the other interesting thing is that I can actually add onto this that it's not just deleting, but also adding. If I add a finite number of terms to the series, then that also doesn't change anything. So we can see here that I can say that, as an example, if we have a series a sub k, k starts at 1 and goes to infinity, if we have this, and we have a series that goes k starts at 10 and goes to infinity, and we have a series that says k starts at 1, goes to infinity, but I'm going to add a number to the front of it, right? Like maybe something like this, like I add something to the addition problem, then these all converge, or they all diverge. By getting rid of finitely many things or adding on finitely many things, I do not change the convergence or divergence. Well, notice that makes something like example 4 a really trivial question. Determine whether the following series converges or diverges. Well, can you kind of tell what series I'm working with here? Take a look at it. Look at its general structure. Look at the numbers it's spitting out. It should be recognizable. Here's what I see. This is like the harmonic series with the first 9 terms deleted, right? Remember that the harmonic series had that shape of 1 over k, k starts at 1 and goes to forever. So here, I've just made a variable switch, that doesn't matter, and instead of starting at thing 1, I've started at thing 10, so I've lopped off the first 9 terms. But since the harmonic diverges, then this series must diverge. So since the harmonic series diverges, then this series must also diverge. Argument complete. Right? So I can see here that this theorem provides us with an opportunity to deal with things or series that are kind of really close to things that we may already recognize, and allows us to maybe say that in certain circumstances, if we ever needed to make minor adjustments to a series, that I could probably easily state that I'm still going to have convergent or divergent, because I know that nothing is going to change there. Now, I'm going to leave example number 5 as a set of questions for you to try to work through, almost like a mini worksheet. If we had been in class for this particular section, then it would have been the case that this would have been stuff you would have had time to work on. So I'll ask you to go ahead and spend some time trying to work through some of these questions. Don't worry if you struggle necessarily with them. That's okay. You just want to use it as a learning opportunity. And of course, you can find the solutions for these up in Blackboard. Feel free to let me know if you come across any questions as well, and I'd be happy to answer them.